I'm Michał, and I'll talk about using Flutter as a frontend for my Android 13 pod that is meant to be used on the Tesla infotainment platform. A few bullet points about me. I'm 26 from Szczecin, Poland. I usually only work on mobile stuff, but I've been tinkering with embedded and the Android open source project for ages. I transitioned to Flutter from iOS 2 years ago, and I'm never going back. Enough about me. It's time to talk about cars. There were a lot of things that I felt were missing in the Tesla infotainment back in 2021. Most of my complaints were about navigation, a lack of guidance sounds in Polish, limited selection of chargers, lack of speed cam warnings, which is very important. I also used Apple Music, so I had to rely on my phone for switching playlists and albums, which was a huge downgrade for me, coming from a car which had CarPlay. This essentially meant that the DJ was always in the passenger seat when we were road tripping. So what is the solution to this? I quickly realized that I could try to provide support for CarPlay or Android Auto without performing any modifications that would affect the warranty on the vehicle. It's easy, right? I've chosen the Chromium browser as a gateway to run an alternative OS by creating some sort of a KVM client. I never wanted to root the car. There still is no support for third-party software. And on top of it, CarPlay requires external hardware that is used for authenticating the session thanks to the Made for iPhone program. And this is essentially where Flutter comes in, because WebGL is supported and Chromium is regularly updated by Tesla with like a month or two delay behind desktop, which is pretty decent. And this also means that WASM garbage collection and WebGPU would also help me in the future to make the experience very close to native. So why on earth would I make it hard for myself and go with Android? I didn't want to reverse engineer any Chinese CarPlay dongles, and not doing so increased my chances for success since I knew Android internals already. It also gave me third-party app support for free, and I essentially utilized the entire horsepower of a tiny computer, which meant that the value for dollar was pretty good, and this made the solution attractive to users. There is also another added benefit, which is that porting standard Linux software to Android is easy if you are patient enough. So about hardware, at this point I knew I had to use a single board platform which is based on ARM. It had to be compatible with the mainline kernel, and open source drivers were crucial since I knew I would have to tinker with them a little bit, because running Android devices without physical displays is not something that is a common use case. I also wanted the board to be powered by USB-C power delivery, since the car comes with 4 ports in the center console, and expansion via USB allowed use of third-party modules like ATE, LTE modems, or third-party CarPlay interfaces, which are commonly used with normal Android head units, which you can buy for any car. I've decided to start with the proof of concept and focus entirely on the software, which means that essentially I solved every problem I could with extra hardware, like having 2 single board computers, one of them doing the image capture and the entire hosting of the front end and the networking, and the other one just doing Android, because basic Android ports for the Raspberry Pi were already available. They weren't perfect, but it was a good base to start on. And I knew that getting it all tightly integrated would take months, if not years at some point. So I I wanted the prototype to solve every potential problem that I might have, like lack of video in Drive or Tesla trying to block third-party apps from using extra CPU resources in Drive, etc. So essentially, the proof of concept, which I made 18 months ago, is not very different technically from what I'm doing today, but it's just much more tightly integrated. The next steps. The proof of concept went viral, so I felt pressured into fixing all the major problems with it and publishing it as is before locking myself down in a cave for a few months, trying to get it more usable and easily deployable. People gave me tons of free QA and positive feedback, which kept me running. And the next goal was essentially getting something that can be installed in a car by the average Joe in around 15 minutes. And I managed to do that. Today, the only thing that you need in order to run this is just flashing a system image on a memory card, popping it into a Raspberry Pi, and plugging it in the car. Nothing else is required. The entire project is open source under GPL3. There was one nasty bug which took 4 months and over 200 comments to solve. It was an integration of a Huawei LTE modem used over USB, which needs to be instantiated in a very non-standard way. But this essentially proves to me that having a platform which is fully open source is the only way to go, because if I were to just use the CarPlay adapter from China and try to interact with it directly without having any sort of documentation, it simply wouldn't fly. Let's talk about the core components which are required to get it all working. The device broadcasts a 5 GHz AC Wi-Fi network, which cannot be disabled at any point, and this is the gateway to the system. I had to cross-compile a standard web server that is normally used for Linux servers, and it acts as a TLS termination proxy for all the WebSockets and my REST APIs, because secure context is sadly required to access most of new web APIs. I had to use IP tables to redirect traffic from a public IP address, which I own, to the device, which is in a local network, because local addresses are not accessible via the browser, because Tesla uses them internally, and there are a lot of things moving away from CAN to automotive internet, because that's essentially how the next generation platform and the Cybertruck work. There is almost nothing being handled by CAN. Everything is done with automotive internet. There is also some DNS spoofing involved, because Tesla used a package called conman to verify that the Wi-Fi network used in the car has internet connectivity, and I wanted the app to work offline, because by default, when you are driving, when you connect your car to, let's say, a hotspot, you get into a tunnel or on a highway where there is no reception, the car will disconnect in like under 30 seconds. So this was a huge blocker initially, and the car is also using Wi-Fi to connect with the Tesla mothership and all of the telemetry services which they use heavily. And I also had to do some clever redirects to get my app working in full screen, because Tesla decided that there are only a few worthy apps like Netflix or Disney Plus, etc., which are available in full screen. So redirecting one port on a IP address which is used by Google for YouTube enabled me to launch the Flutter app in full screen and do the redirect to my domain after everything is launched. I had to do some modifications to the Android frameworks itself, mainly to system UI and settings, because everything that relates to connecting to Wi-Fi, disabling tethering, etc. It all had to go because this was the only Wi-Fi is essentially the only way to interact with the device because it doesn't have a screen. I also did some small changes in the kernel to get standard USB networking devices instantiated in a way which would enable the system to treat them as a valid internet source for tethering, which is normally restricted only to the data plan that you have on your phone. Since data packages, especially in the US or the UAE, are very expensive. We are talking like hundreds of dollars for a huge package per month. It was a huge thing for me to add support for tethering back from Android and iOS phones back to the single board computer with USB. So essentially, if you want to use Tesla Android, you can simply plug in your phone and you'll always have internet. And those, on top of the kernel changes which were required to initialize those devices, there are also no UDEF rules for Android. So all of the devices had to be instantiated manually by default, and I got around it by creating a small system service which uses libUSB to do some manual polling. Okay, now the most interesting part, which most of you are interested in, the Flutter frontend. There are some specific things to running third-party apps in the Tesla ecosystem. You need to have some sort of a health check API to synchronize all of the transport components in order to stop them from maintaining connection with the device when it is not accessible. And after the connectivity is restored, the page which hosts the Android OS viewer module is simply pushed back into the navigation stack. All of the qubits transport components gets injected, and everything starts as if the app was reloaded. There are also several limitations when it comes to WebGL, especially on older vehicles which do not have the powerful Ryzen infotainment system, but a very weak Intel Atom processor. On the left side of the screen, when you drive the car, there are full self-driving visualizations always being displayed to show you the surroundings, and they are very heavy on the GPU. So it is very easy to get out-of-memory errors from Flutter when the car is in drive. A easy fix I found for it is limiting the amount of surfaces which are used by CanvasKit. And it's very, very important to avoid unnecessary redraws because the frame rate can very easily dip into like low 30s if you don't do it. The most important component, and the component which took me the longest to develop, is the virtual display. It relies on a headless operation mode, which is exposed by the DRM HW composer in Android. I added a possibility to dynamically resize this headless display using system properties which are exposed by the REST API. Raw RGBA frames are taken directly from the Surface Flinger. They are encoded with a hardware-accelerated encoder, which is provided by Broadcom and is specific to the SoC used. This means little to no CPU overhead and constant frame times. WebSockets are used for transport, and I also did a little trick in the Android framework which enables the capture of DRM content by removing overlays which are drawn over the secure layers. And it works because Android simply draws a black box over the app which is displaying DRM content. It is still being normally drawn. On the front-end side, it's much easier. There is a simple layout builder which captures the size of the window, and this gives you the dynamic resize. It is managed by a single qubit that calculates a optimal resolution after each size change, and it sends it to the device. Additional configuration is also available. The user can choose a maximum resolution and select a renderer. I've seen best results with WebGL in combination with web codecs. There are also 5 other alternatives available if Tesla decides to break one of them randomly, and it sadly happened over the last year a few times. The virtual touchscreen is much more straightforward since it worked very well from day one, and I carried it over from the proof of concept. There is a small kernel module which exposes a character device that can consume multi-touch events from the browser via a small proxy in the Android operating system. Flutter frontend essentially maintains the state of each of 10 multi-touch slots and generates events which are compatible with a Linux multi-touch protocol, which is relatively simple. I also had to use the browser audio if I wanted it to work in full screen because Bluetooth audio is not available there. I've decided to stream the 48 kilohertz stereo PCM stream directly from the framework just after it's generated and before it gets processed by the hardware abstraction layer. It uses the same WebSocket transports both on the embedded and the Flutter side. This feature made lossless audio playback possible in all of the cars. And I simply feed the raw bytes directly to the audio context via JS interop. It's pretty straightforward. I also managed to get hardware GPS supported because the module present in the car on the autopilot computer is accessible in the browser. And I've observed that polling it manually with a high frequency always provides a fresh set of coordinates, which is not always the case, especially on mobile platforms. So that's how Tesla implemented it. It's a gift for me. And this location data is fed down to Android with WebSockets, and those events are consumed by a modified version of the GPS hardware abstraction layer used by the Android emulator. So it's essentially the same kind of GPS support that you have on the emulator. The phone essentially thinks that it has real hardware GPS support. There is one disadvantage because speed is not exposed by the web browser, so it needs to be approximated based on the changes in coordinates, and it's not always very accurate, especially when you are driving slow, because there is a lot of jitter on GPS. When it comes to the Android port itself, it comes with Google Apps. Normally, they are all functional. I had to inject a fingerprint from a pixel to satisfy device attestation checks, which I use by SafetyNet. But ultimately, most of the apps run without issues. All DRM, both audio and video, is supported. The OS is not rooted, so like a normal OEM implementation, and Android verified boot is implemented from the bootloader back to the system layer. I've also enabled seamless AB over-the-air support, which means that system updates are installed when the car is being driven, so essentially in the same way as it works on Pixel phones. A few things about the development process. I use 3 Mac Minis for CI, and everything is built on Jenkins, and every component that can be built on ARM is built on ARM because it's much faster. The entire release flow is automated, and given that I wanted each build to each push to the main repository to trigger a full build, I got around very long build times by using overlay file system to generate workspaces for incremental builds. And this is a huge space saver because one Android build system is like 350 gigs without after a clean build. I use a real hardware development kit, which was provided to me by the Tesla routing community, and it's helped significantly because I can do, I essentially have full SSH access, and I can profile the app like I would normally do it on my computer. I also use Sentry for capturing logs from my users, and it works very well. But I had to build the app in profile mode in order to avoid obfuscation issues, which are still a thing on the web. And on top of it, the development kit is fully rooted. It also has access to software updates, so I can jump the queue. And the moment Tesla pushes out a new build, like every 2 weeks or so, I have it like a month earlier than in my car, which is helpful because Tesla has a engineering culture where they move fast and break tons of things in the process, and there are tons of regressions. And Chromium is, up until now, it wasn't a very important component in the system, but right now Tesla is also using Chromium to build system apps. Apple Music, Spotify, and others are powered by Chromium, which greatly benefits how Flutter behaves on the platform. A little bit about the results. The project website gets over 250,000 hits each quarter. There are over 5,000 daily active users on every continent, and this is significantly lower than it could have been because it's impossible to get single-board computers right now due to the chip shortage. The project in various stages was featured by most major tech media outlets all over the world. Given the huge community, all the project-related costs like dev kits, CI machines, tools, 3D printers, you name it, it was all covered by the community. And I've learned a lot because there are tons of technologies used, and there is always something you can learn. Yeah, so this essentially brings my presentation to an end. Those are some of the pictures which my community members sent me. Most of them are from California, as I see it, but that's how it behaves in Drive. You essentially can run any type of software you want in the car. Thank you.